Okay, guys, new unit. Unit number 7 is going to be moles and stoichiometry. All right, so this is we're going to talk about the math of quantities, or the science of quantities in chemical reactions and all across the board. So we want to define a really important concept. Okay, so going forward, if you can understand this one concept, it can be used to solve all types of problems in chemistry. Um, so let's get to it. When we talk about quantities, again, this strange word stoichiometry, we can begin with that. Okay, so stoichiometry. So stoichiometry, I know it's a strange sounding word. Uh, and again, that's going to be the science of how we do quantities. Okay, you may be wondering, what's that kind of word? Crazy. So really what we do is we study the quantities and calculations when we have to deal with chemical quantities. We haven't done much with chemical quantities in this class, but that's going to end because we're going to be using it now and all the way through the rest of the course. Okay, and again, if we examine this problem, it's like, so what is really the problems when dealing with chemical quantities? Okay, and again, if we look at this, we realize that number one, that molecules and atoms are way too small to see, right? So you can't see them. So when we deal with, quantities in real life that are larger particles, such as pennies or eggs or staples or, any average size object, it's easy because we can count them. We can see them really easily. All right, so that's the problem. Okay, and secondly, is that reactions, remember we talked about the reactions unit, that we talked about collisions of particles. So reactions occur depending on the numbers of atoms, like and molecules. So when you balance a reaction, we're really balancing the numbers of particles, right? If you think about it, if you think of a reaction that has like 4 carbons on one side and 4 on the other, when we balance, we're really balancing the number of particles. Now, if that really matters and reactions occur on the numbers of atoms, and they're in fact too small to see, then how do we really count them? How do we really know that they're there? So this becomes a problem, right? So if you see why there's a problem here, you'll understand what we're up against. Okay, and I want to bring up a baking recipe, which is very similar to a chemical reaction. So if you took 1 cup of sugar and 3 eggs and 2 cups of flour to make 1 cake, you can see that these coefficients in this balanced reaction are the ratios of the recipe. So almost the recipe is similar to the way a balanced reaction works in the fact that you have 1 of these, 3 of these, and 2 of these would make 1 of these. So, but this is easy in a baking recipe because number one, we can count the cups, we can count the 3 eggs, and we can count the 2 cups of flour, and we can count the fact that we made 1 cake. But let's just say, for instance, that we couldn't count the number of eggs. Now what do you do? Or what do you do if you have only 2 eggs? Or what if you wanted to make 2 cakes? How much flour would you need to make 3 cakes, right? Or if you had 5 cups of sugar, how many cakes could you make? So all of these different type of questions that we would go through in quantities, we can end up solving. Okay, so if I ask you the simple question of how many eggs for 3 cakes, well, you could see that one cake needs 3 eggs, right? So that if we needed to make 3 cakes, if you're timing this by 3, you would then need 9 eggs. Now, again, that's easy, right? Because we know that there's a 3-to-1 ratio of a comparison. 1 cake needs 3 eggs. So if you're multiplying this by 3, everything in the recipe must be multiplied by 3. This is identical to what you do in a chemical reaction. But again, we have this problem of too small to see for the particles. All right. So how do we express quantity anyway? Like, if we go back to the beginning, we say, okay, how do we actually form the quantities of anything in life? Like, how do we communicate quantities? How do we do this? And I always think about apple picking or fruit picking. You can think about it any way you want. So anything you buy something in the store, you always deal with quantities. So how do we actually express the quantities of things when we buy them? Okay, so let's just say I went apple picking and I have 24 apples. Well, how would I actually pay for these apples? And number one, I can pay for them by mass. I can say, well, how heavy are those apples? Maybe I have 5,000 grams of apples, or maybe 5 kilograms. You can even think of this as being 5 kilograms. And you could pay for those apples by kilogram, right? You could weigh those 24 apples. I'm not saying that it's exactly 5 kilograms or even 5. I'm just saying using these numbers for comparison. So you could say how heavy something is. So you can do it by mass. You can also do it by volume, right? You could put these apples in a bag, or you could put them in a bushel. These little like these wood baskets. Okay, and you could say, okay, it was 24 apples. Maybe they, if I weigh them, they're 5 kilograms. But also, if I put them, they could fit in a basket. So that would be by volume. All right, so we can pay things by volume. I mean, how many times have you bought a box of this, or a case of this, or a bottle of this? That would be in volume. Or we bought a pound of something, a pound of cold cuts, or a pound of turkey, or ham. You would buy that as far as mass, right? Okay. Or we can count those particles in groups, right? We could take those 24 apples and we can buy them by the dozen, and we can ask ourselves how many. So the questions is how big, how heavy, or how many. What are you really doing? You're measuring by mass, or measuring by volume, or you're measuring by the number of particles. Okay. Now, depending on the object, or depending on the situation, you would use these one of these three types of ways to measure. Okay, the same thing, we do that when we deal with chemical quantities. We can count things, we can find their mass, we can find their volume. The problem is apples are easy to count because they're large objects. So this is going to be a little tough to do because the molecules and atoms are too small to count. Okay, so we're going to be a little out of luck with this. However, this is the most important part because this is how things react, right? They react because there's a certain number of particles. For example, sodium chloride has 1 sodium to 1 chlorine. We really don't worry about how much they weigh and how much their volume takes. We just, when you form the compound, you have 1 and 1. So how do you deal with this? Okay, so this is the next part. So pay attention carefully to this. Now, what's important too is we can also convert any sample of these to any other by looking at the fact that 24 apples equals 5,000 grams. 24 apples equals 1 basket. 24 apples is 2 dozen. So we can almost make these like, remember when we went back to our dimensional analysis, we talked about conversion factors. So it's easy to convert this, right? If I had 12 apples, I would have half a dozen. I would have a basket. I would have 5,000 grams. All right. So I just want you to just think about this little abstract thing. Let's just say I look at the mass of elements, and I want to look at the comparison of two elements. I want to look at the comparison of hydrogen to oxygen. And the reason I'm using hydrogen and oxygen is because hydrogen has a mass of 1, right? The mass of hydrogen is 1. So if you look up hydrogen on the periodic table, basically its atomic mass is 1. And if you look up oxygen on the table, you'll see its atomic mass is 16. So that's what I'm going to go with. Now, this is 1 for 1. So let's just say I had the mass of 1 single hydrogen atom, and I compare that to 1 atom of oxygen. Okay, so if you agree with this, you would say that the mass of a single oxygen atom would weigh 1 AMU, 1 atomic mass unit, for 1 proton. Now, the mass of 1 oxygen atom would be 16 AMU, and again, because the atomic number is 8, you have 8 protons, 8 neutrons, and that's where we get the 16. Again, just going back a little bit, but so one of these weighs 1, one of these weighs 16. So it's almost like the comparison of a softball versus a bowling ball, 1 of each. Okay, now here's where it gets interesting. Let's just say I then multiply by 10. So now I have 10 H's and I have 10 O's. How much does the 10 H's weigh? Well, 10 times 1 AMU would be 10 AMU. That would be the weight. Okay, and now I'd weigh 160 if I had 10 oxygens. Now I'm keeping these particles the same. That's the key. Same number of particles. Okay, same number of particles. Really important here. Same number of particles. Okay, now let's just say I did this again. Let's just say I measured out, well, even before I do that, let's just say I went to 100 of these and 100 of these. Then I would have 100 AMU, and I have 1,600 for oxygen. And let's just say I went to 1,000,000. Then I would have 1,000,000 of these. I would have 1,000,000 AMU. Okay, and you guess it, 16 million of these. So as I start to get more and more particles, the AMUs get heavier and heavier and heavier. What I want to do, I eventually want to get to a point where I have so many particles that the AMU turns into grams, right? Because if I can turn that into grams, then I can put them on a scale and I can still count them. And that's what I want to be able to do. So I'm going to jack this all the way up. until I can measure out 1 gram of hydrogen and 16 grams of oxygen. So I would still have the same number of particles. Okay, what if I do that? Okay. Now, what's interesting about the 1 gram and the 16 grams is that still matches the periodic table. But what I've done, okay, is I've changed the AMU, which is something we can't weigh on a scale, into something I can use in a lab, right? I can weigh things in grams. Now, if I go to if I go to a, chemical bottles and I just weigh out 1 gram of hydrogen and 16 grams of oxygen, okay, I can be sure that even though I can't count the particles, I do know those particles are the same. All right, so what is that? What is that number of particles where a single one, a number of these and a number of these turns into grams? Okay, because now if I keep it in grams and I keep those same on the periodic table, I have the equal number of particles. So what is that number? Okay, so what I want to do is introduce a special term to you guys. It's a special number, and this is very interesting. Okay, we will have, when we have that atomic mass in grams, if we take that atomic mass, so for example, 1 gram of hydrogen or 16 grams of oxygen, okay, we're going to have something called a mole. And a mole is the number of particles that you get when you weigh out that amount in grams from the periodic table, okay? And the number of particles in that amount is huge. It's a huge number of particles, right? Because an AMU is so small. The number of that particles is going to be 6.02 times 10 to the 23rd particles, okay? And the name of that is called a mole. So a mole is that number of particles, just like a dozen would be 12, a case would be 24. We use a special name. Okay? And this is called Avogadro's number, after Amadeo Avogadro, who did work with finding equal numbers of particles. And again, a little more about him later. Okay, so there's the mole. Okay, so what we're going to do is we're going to use this mole to track the number of atoms, molecules, or ions, because we can't count them directly. We're going to count by weighing. Okay, if you take this number, 6.02 times 10 to the 23rd, and you actually write it out as a number, you would get this kind of number, a huge, tremendous amount of number. So for example, if you wanted this number of hydrogen atoms, you would weigh out 1 gram. That would be 1 gram of hydrogen. If you wanted this amount of oxygen atoms, you would weigh 16 grams of oxygen. So it's really easy. Go to the periodic table, take that number, turn it into grams, and you have this many particles of that substance. Okay? The name of this mass is called the gram formula mass, otherwise known as the GFM. Okay, the gram formula mass is the gram mass, so it's mass in grams, of a formula of a substance, which is going to be 1 mole, okay, which is going to be a 6.02 times 10 to the 23rd particles or particles of that substance. And again, the particles could be atoms, moles, or ions. Okay, so that's the name of that mass. Okay, and again, in a lab, listen, we can't count particles in a lab. It's too small. So what we'll have to use is grams or liters, okay, in lab work, and then convert it to particles if we need to, okay? Now, again, this is exactly what we're doing. We're counting by weighing. We're weighing our particles, and we're counting them. Okay? This is very similar to, if you remember back at sometimes carnivals, or, maybe if you go to a carnival, or any of the amusement parks or something like that, or you go to a boardwalk or something like that, where you have the little marbles in a jar, right? And you have to count the number of marbles in this huge jar. And if you can count all the marbles in this huge jar, you can get an idea of, what this is. Or if you want to count a lot of pennies at one time, right? So you have a whole jar of pennies. Well, if you weigh the pennies and weigh the mass of 1 penny and divide, you can get an idea of how many pennies are in the jar, because you know the mass of 1 penny. It's a similar idea here. Okay? So 1 gram of hydrogen would be 1 gram per mole. Okay, so again, this is the GFM unit. The unit is 1 gram per mole. If you had 16 grams of oxygen, you had 16 grams for every mole. Again, a mole is 6.02 times 10 to the 23rd. So this is the unit for this GFM. If you had 64 grams, you would have 64 grams of copper, 64 grams per mole, again, per 1 mole. So this is how you, and again, these numbers are from the periodic table. These would all have the same number of particles because you got them directly off the table. Okay, so that's what a mole is. Okay. So if you had to do this for compounds, it's actually kind of easy. We can do this together. Now, what I would do is I would use this as a simple chart. I like charts. I think this works great. So if you had to find the mass of 1 mole of this, you simply go to the periodic table. But in a compound, you simply would just simply add them together or find their sum. So what I like to do is I just like to set up a little chart. I say, okay, there's H and there's O. Okay. And if you look at the formula, you see there's 2 H's and there's 1 O. Okay. And then what I'll go is I'll go to my periodic table and I'll look up my masses on the periodic table. Well, the mass of a hydrogen in the periodic table is 1 gram per mole, right? So 2 times that would be 2. And there was 1 oxygen in this formula, so 1 times 16 grams per mole from the table would be 16. Okay. So I would add that together and I would get 18 grams per mole. Okay. And that would be the that would equal the GFM, or the gram formula mass of water. Okay, let's just say I wanted to do this for ammonium sulfate. Again, watch your counting here. Watch the family that you have in here in parentheses, this polyatomic ion. Make sure that you know this multiplier goes for this and that. Okay, so I'm going to have my N, I'm going to have my H, I'm going to have my S, I'm going to have my O. So again, I'm going to use my numbers here. So I'm going to have 2 N's, I'm going to have 8 H's, right? I'm going to have 1 S, I'm going to have 4 oxygens. So let me just double check that. So two N's, 8, 30, and you have now S is one of them, okay, and I have 4 oxygens. So now I'm going to get the GFMs from the table, okay? From the table, nitrogen is going to be 14 grams per mole, which gives me 28, okay? I'm going to have 8 times 1 grams per mole. And again, after a while, you end up remembering these, okay, which would be 8, right? We can get rid of that. You can just make these numbers the same, okay? If I look up sulfur, sulfur is actually 32, right, grams per mole. So I'll make that 1 times 32 is 32, okay? And 4 oxygen is 16 grams per mole, okay? And I have 64. All right. Now I'm going to get rid of my trusty calculator. Again, you want to have a calculator for all of this, guys. Make sure you have that information ready to go. Okay, so I'm going to sit here and I'm going to calculate it. So I have 28, okay, plus my 8, plus my 32, plus my 64, okay, and I'm going to get 132. So I'm going to get 132, and you guessed it, grams per mole. All right, so it would be, again, my GFM. Now, look at these two numbers, 18 here, 132 here. Both of these have the same number of particles because you're looking at 1 mole. Really important. Okay, so let's just double check this. 28, 2 nitrogens, 32, 64, 132 looks good. Okay, so next thing, let's just say how many grams are there in 1 mole, okay, of aluminum hydroxide. I want you to notice one thing. Mass of 1 mole, gram formula mass, and grams in 1 mole are all saying the same thing. Again, it's a gram formula, grams in a mole, mass of 1 mole. 3 ways to answer the same thing, okay? Aluminum hydroxide. So again, this is a little different because I'm going to have to find my formula. Aluminum is plus 3, oxygen, hydroxide is a polyatomic ion, crisscross. Here's the crucial point. Have to get parentheses, otherwise you're going to get this wrong. Please make sure that you write correct formulas. No correct formulas, no correct GFM. So we have aluminum. There's one of them. In the table, aluminum is 27. We'll take 27 times grams per mole, and we'll get 27. Okay, oxygen is going to be, there's 3 of them, right? So see that? So yeah, again, AlOH3. The 3 goes for the hydrogen. The 3 also goes for the oxygen. So it's going to be 3 of them times 16 grams per mole, which is 48. Okay. And then oxygen, there's 2 of, hydrogen, sorry, there's 2 of them times 1 again. You're probably getting used to looking at hydrogen being 1. We have 2. for a grand total of, let's get it together and say 27 plus 48. I'm sorry, there's three hydrogens for 3. Very easy to make a mistake. In fact, more people make mistakes on GFMs than anything else. Okay, 27 plus 48 plus 3 is going to be 78. Okay, so in this case, we're going to get 78 grams per mole. Okay, so that again is your GFM. Okay, so very, very easy, guys. It's not hard to do. It's just you have to understand, okay, what's going on. Okay, so that's really what it is. Okay, that's what we got so far. Okay, I'm going to stop here. Again, just remember, please remember that we can't count. You can't count particles. And particles are really important for reactions. In fact, the reason reactions take place is because they need the correct number of particles to do this. Well, how do we actually count the particles? Well, we really can't directly count them. We can't do that. So what do? We have to collect them in groups. Okay, very similar to going to the supermarket and buying eggs. When we buy eggs, we generally buy a dozen eggs. We buy them in groups because eggs are very small. Okay, if we were to buy thumbtacks or we were to buy staples, we would go to the store and we would buy groups of these particles because they're small. All right, so the only thing we can do as chemistry is use weight or volume. Okay, so we've taken care of the weight today. If you want to count particles, simply go to the periodic table and count out 1 mole. And you can do that very easily by weighing the sample and taking the gram formula mass. Next up, we'll talk about the volume of the sample. All right, and we'll do that in another clip. All right, great, thank you.